Okay. Octavio, can you hear me?
Yes, we can hear you. And we can also see the slides.
Very low. Okay. Everything is visible, Octavio?
Yes, I can see the slides. I can also see you and hear you properly. I don't know if everybody else is having problems.
Okay. Just for the students that are following online, I ask to when they need to talk or ask a question to turn on the microphone and ask the question, because I don't look at the chat. If you are not okay with that, just let me know and I can change and have a look at the chat. Fair. Just write on the chat now whatever you prefer. I can have a look. So first, some organization thing. I put online on the Moodle the installation procedure for the virtual machine. I want to ask you if you can have MATLAB for the first lab, while the virtual machine will be used only for the second, the fifth lab. Do you have the possibility to have a MATLAB license with the university? It's fine. Okay. Okay. For the ones that don't know, never saw MATLAB, use that. Octavio will upload an introduction tutorial. We will use a tool of MATLAB that is called Simulink that allows us to do simulation of dynamical systems, like the one that we will build. It will be the one of a mechanical load linked to an actuator, and the actuator is a DC motor. We see today the modeling of this DC motor. And why we use MATLAB, even if I'm not a fan of non-open source software, and MATLAB is non-open source, so you need to buy if you work in a company or by yourself. I think MATLAB is quite handy to design control systems, to design a controller, and comes with a lot of simulation aids. You don't have to worry about the implementing yourself the integration scheme. So it's good to use that for quick and dirty trials. But in general, we later on we try to use only Python. Okay, I have a laser pointer now. So in the previous lecture, I will do a quick summary here. We talk about vision sensors. So that sensors, exteroceptive sensor that takes care of acquiring a 2D image from the environment and to do reconstruction from 2D image of the 3D map of the environment that can be used by the robot to localize itself or to do, for example, activities like visual servoing, which means tracking an object and following an object with the end effector. Or in case of like the robot moves and decide where to put the foothold in the safest places to don't lose stability, for example, avoiding holes. Then I was giving you some signal processing basics, going through the non-idealities of a digital implementation of our controller, which means that when we implement the digital controller via software, we can have some delays due to the digital implementation, quantization errors, and also some aliasing problem if the sampling frequency is too low. And then I was starting to introduce the actuators for robotics. And we actually introduced only the pneumatic and hydraulic actuators. And now we come to the most important ones that are electrical motors. There were two questions from you. I was documenting myself, coming with a response. And the question was that what if why a laser, the laser sensor of a LiDAR has problem whenever it comes with a reflective surface. And the reason is that even an opaque surface is reflecting the laser because we can see the dot, we can see the point of the laser, right? So, but it's reflecting in all directions, but you still can receive the return of this reflection, partial reflection, via a sensor to capture this reflection. But whenever there is a reflective or even worse, a semi-transparent, like a glass surface, then this is very bad because they can reflect with a precise angle, so the sensor cannot detect it. Or in the case of a glass, they can bounce many times and create aliasing. This is a situation in which you have a LiDAR, a laser pointing a stair, and behind the stairs there is a window, and you see that there's a brown detection of another stairs, while in the reality there is only one stair. And in general, the laser contains only a receiver, as a receiver following one point. You can find more resources on LiDARs on the Wikipedia page. It's not bad, it's quite detailed. Then the second question was about the order of a digital filter. And in this case, we can define the order of a discrete time filter as the highest discrete time delay used in the input-output equation of the filter. So if you look at the transfer function of the filter, you have this is the zeta transforms, the z transform, which is the same as the Laplace transforms for the discrete domain. And in essence, this transfer function can be one-to-one mapped into a difference equation, that like the one we saw, that was like y of k equal to something that depends on past values of the inputs and past values of the output. And the order, it's a maximum delay or of input or output that is in this difference equation. And it normally it corresponds, is equivalent to the order of the denominator of the transfer function, or the polynomial of the transfer function. And for example, you have an example here. I don't know if you can see it. Wherever we have the output, this function of the previous actual input of the previous input, and also of the output of the previous sample and the previous past sample. In case of a moving average filter, these filters are called finite impulse response filters, FIR, non-recursive, and their order is equivalent to the number of samples in the window. So if you have a 10 sample window, we have a 10 order filter. they are called finite impulse response filters because they have if you give an input to them, this impulse will reflect to the output till a certain time, and then it will disappear. So you will see that the response becomes zero after a certain time, so of limited duration. And in general, the output of a filter of a finite impulse response filter is a function only of the input signal. So if you think about our moving average signal filter, sorry, it's a weighted average with this B coefficient of the input. While the other class of filters that, for example, the low pass filter that we saw belongs to the class of the infinite impulse response filters, and they have a response to the impulse that does not become exactly zero, but it gradually, after an infinite time, it will become zero. So you have that the response will be infinite in time. And they are called recursive filters because they have a feedback from the output to input. As in the previous case, the example you saw was like this kind of filter. And as this kind of finite difference equation, you see here that we not only have the inputs but also the outputs in the difference equation. So in this case, you need to work out the transfer function and see the denominator to check the filter. But in general, it's the number of oldest samples, either in input or output, that is in the difference equation that tells you what is the order of filter. It's clear? Everything's clear? This was just a question of yesterday. Now we can start talking about electrical motors. So electric motors is an actuator that converts electrical energy into mechanical energy thanks to the interaction between some magnetic fields in the motor that are interacting with the current that is flowing into a coil. A coil is just a winding, like in Italian is avvolgimento. It's an inductance that is present in the electrical motors. You will see a picture of that. And the advantages of these electrical actuators are that the power supply, which is usually an electrical power supply, either a monophase or three-phase, it's usually available everywhere. They are low cost and they are easy to control. This is one of the biggest advantage of electrical actuators because of their linear dynamics, and they are also reliable and have high efficiency in converting electrical power into mechanical power. They're also easy to maintain, and they don't create pollution like hydraulic actuators that I told you that are creating leakage. So there are drops of oil once in a while appearing in your robot. There are some also disadvantages in electrical actuators. One of the bigger ones is the overheating of the coil. In static condition, whenever there is a big current, we will see what does it mean, why in static condition you have big current. You can have that the Joule losses that are due to this current passing into the coil, they create some dissipative heat. So this will increase the temperature of the coil, and at some point can cause a loss of insulation. So the coating that it's covering the coil, it's melting, and then there is the possibility to create a short circuit between the coil wires and to burn the motor, in essence. Then the other disadvantage is that they have low power to weight ratio. You remember the hydraulic actuators? How were they? Did they have a low or high power to weight ratio? You remember? High? Yes. So this means, what does it mean? For example, low power to weight ratio. That what is the main issue with this? Yeah. Yeah, correct. So big motor, big weight, bigger inertia, and then again to move, you need even a bigger torque. So even a big motor is a chicken and egg problem. And another disadvantage is that some models you will see require some more complex control laws, in particular the BLDC motors. Yes.
What means power supply is
That you don't have to have a pump like a big 1 cubic meter pump, like in case of an hydraulic robot that you need to have close to the robot. You just plug on the wall. There is a in the labs there are available either 380 volts three phase alternate current or monophase 220. So it's, in that sense, you don't need a specific device to create the supply, which is in the case of hydraulic actuators, the supply is the pressure, is a pressure energy. So you need to create this. And between the categories of electrical motors, we can discriminate between AC motors, where AC stands for alternating current motors, and DC motors, that stands for direct current motors. And AC motors rotate at constant speed, let's say, mainly, that is proportional to the alternating current frequency. You know what's the frequency in our alternating current monophase or even three phase in the industry that we is normally used? You know how much is that?
60 hertz.
Yeah, in Italy is around 50. Some countries they might have a different frequency. So it really depends on the country. Then the AC motors, they are divided in two categories: synchronous and asynchronous motors. The synchronous motors are also called induction motors. And the synchronous motors have, so when I say coil or windings, do you know what I'm talking about? They're the same thing. They are the inductance that are rolled around the rotor or the stator. So the stator is usually the outer part, while the rotor is the moving inner part. And in a synchronous motor, the rotor and stator are powered separately with some power supply. We will see how does it look like. And in general, the speed of the rotor is the same as the statoric magnetic field. We will see this later on. In case of an asynchronous motor, instead, the rotor is, so in case of a synchronous motor, the rotor could be a permanent magnet, either a permanent magnet or a coil, while the stator is usually are free coils connected to the three phases power supply. While in case of a synchronous motor, the rotor is always a coil, cannot be a permanent magnet. And these motors are usually inexpensive and efficient They're used in the old washing machines, the one that have a fixed frequency. And as I said, the rotor is not powered. And because it's a coil, the electric current in the rotor that is needed to produce the torque is obtained via electromagnetic induction from the rotating magnetic field from the stator. So the stator creates a rotating field that couples on the rotor coil and generates an electromotive force, and this creates a current, and this current creates a magnetic field that it's attracted by a rotoric one. But the peculiarity is that to have a magnetic field in the rotor, you need to have a difference in the speed of the rotor and the statoric magnetic field. And we will see why this, because otherwise you don't have a changing magnetic field in the rotor, so a flux. Instead, the DC motors that are powered with a constant DC current and voltage, sorry, a constant DC voltage. And an example of a DC motor is this. You have the stator that is a permanent magnet that creates a magnetic field in this direction, and the rotor is like a coil that moves. And they have large torque and speed range. They can change the speed. And there are two classes. The first, the oldest construction of DC motor was with brushes. So what exactly like this in the figure, the stator was a permanent magnet and the rotor is an electromagnet, a coil. And these brushes, they were bringing the supply, the current to this rotoric coil, and they were switching polarity. We will see in detail how this works. And changing the polarity was allowing to have a continuous current supply and still keep the rotation of the rotor. And the problem is that while switching these polarities, there were sparks, and because of very big change in current that creates this, due to the inductance, this very high voltage across the inductance, and this creates a disruptive, like a lighting spark to change the current. And this at some point brings to wearing of the brushes. While the last models, they are brushless, and this time the rotor is the permanent magnet, while on the stator there are the stationary coils. And the trick this time is to use control electronics to power the switched polarity of these coils such that they create a rotating magnetic field that attracts the rotor, the permanent magnet on the rotor. And they are very flexible. You can achieve variable speed and variable torque, and the brushless motors are the mostly used in robotics. In the case they are also coupled with a transmission and an encoder, they are called even with servo motors. So whenever you can control there's a single package with the encoder and the transmission. And the idea, as I told you, is to create a magnetic field that's like a donkey that follows you think the donkey as the rotor, and the statoric magnetic field as the carrot, if the rotor is following the magnetic field of the stator. Finally, we have the last category of electrical motors that are the stepper motors. And these kind of motors are very simple. They are used normally in printers, in plotters, and they move. They are slow in general, and they have a peculiarity of moving in precise and discrete steps by energizing one pole at a time. So if you energize this coil, the rotor will align to that position. If you energize another coil, it will align to the other position. So their resolution in terms of position will depend on the number of coils that you have on the stator. They are very easy to control. They have low efficiency because they always draw maximum current, and their driving idea to move them, as I said, is to apply different voltages at the terminals of the coil, and doing this in a correct sequence, the rotor will move in a direction. If you change the sequence of activation of these coils, the rotor will move in the other direction. This is usually done with a microcontroller or an electronic circuit. And the important point is that if you require more torque than is able to generate the pole, then the stepper motor will lose the path, so will slip and move in another position. Okay. This is sorry. This should have been presented before because it's part of the hydraulic actuation kind of actuator. It's called electrohydrostatic actuators, and the peculiarity of this one is that there is a pump, in essence, a servo motor that moves an hydraulic pump, and this pump, without valve, rotating in one direction or in the other, creates a pressure in one of the chamber or in the other chamber of the piston, and will move the piston in one direction or the other direction. So changing the rotation of the pump will create a pressure in both chambers. The problem of this actuator is that it requires a variable speed pump, so not in the case, as in the case of hydraulic actuation, where we have a fixed speed pump that creates the pressure and we recirculate the oil that we don't need on a relief valve. This is the way we create a constant pressure source. Here we have we need that the pump is able to change the speed, because if you want to be fast, we want to rotate faster the pump and create move the oil faster in one direction or the other. And depending on the flow, the axis extends or retracts. Normally, these actuators are linear pistons. And the problem of these actuators is that they depend on the speed of the pump and on its ability to change its velocity and its direction. And since everything has mechanical component have inertia, they are quite slow, but they can provide big force. So I think this kind of actuator are used, for example, in the airplanes when in the landing cart to retract or extend this kind of or in the flaps. But I'm not sure. I'm not sure about that. Then we have series elastic actuators. Sorry, there's a mismatch in the animation. Series elastic actuators contain an elastic element, like a spring, that is in series with the actuator itself. That most of the time is an electrical motor. So here we have the electrical motor, we might have some gearbox, some transmission, and then we have a spring, and after the spring we have the load. And the advantage of serious elastic actuators is they provide tolerance, big tolerance to impact loads, and they have low mechanical output impedance, so they are compliant. Whenever you touch them, you feel them, that you can back drive them. They can do some sort of passive energy storage because you can compress the spring and you can store some energy in the spring as elastic energy that can be released in a second moment. And this is the reason for which people in robotics for 10, 15 years were using this, and they were justifying these actuators because of their human-robot interaction compliance, so that whenever they need to interact with humans, you don't create big forces, and with the fact that you could store energy. But the real truth is that nowadays very few people use them, and the problem is that yeah. So I ask you, do you think it's easier to control, for example, the force on when pushing on a rigid wall or on a soft wall? Why?
You don't have to take into account the elasticity of the position.
There is always some elasticity in the wall, even if it's perfectly rigid. The thing is that this elasticity or stiffness, it's very high. So for every motion of the actuator, the force, it is the integral of the velocity, because the force is, the elastic force is K for the deformation, but you could see the deformation as the integral of the velocity. So the displacement.
Michele, can you repeat the answer? Because the people that are listening to lecture cannot hear the answers.
Yeah. So the answer is that if you push against the wall, what was exactly your answer?
That the wall has a different the elasticity of the wall. You have to take into account also while controlling the system.
Yeah. So the even the most rigid wall has some elasticity, but this elasticity is low in case of a stiff wall, and because of the characteristic dynamics of a spring, you see that for a stiff contact, you have that the force can build up very fast because it's the integral of the velocity. So if you push, if you move against the wall, the force will increase very quickly. If you move away, it will decrease very quickly. So it will be very reactive. While if you have a very soft contact compliance, like in the case of a serious elastic actuator, then you move the actuator and the force will build up very slowly, and as well will decrease very slowly. And this creates issues in the bandwidth. So you're not able to control the force. You have a limitation in your ability to quickly control the force that is represented by the bandwidth of the actuator, in this case, the force bandwidth, that is limited by the passive spring dynamics. Up to, there is not much we can do to speed up the bandwidth of our actuator. And another problem of serious elastic actuator is that if you want to measure the deformation of the spring, you need an encoder on the on the load side and an encoder on the motor side. So you need two sensors and not one. And this is an example of a series elastic actuator with a spring. And the spring you see is not necessarily an element as we usually know, but it could be like a very strange shape that gives you elasticity between the outer ring and the inner ring, for example. Yeah, series elastic actuators are useful, for example, for this robot that needs to really use energy for jumping and store energy, because from one jump and the other, they can store energy in the spring. And this is one of the nicest hopping robots, and it's called Salto. While also in human-robot interaction, you can see that series elastic actuators are used to interact with humans, and to avoid the problem of the spring that is only if you have a spring, you will have infinite oscillations. People implemented some damping strategies with piezoelectric to remove the continuous oscillation and to have compliance, but also come back without any overshoot. So this is a work, I think, from the DLR guys, and it's very nice because you can hammer it and reject big impacts. Finally, the horn is the last trend nowadays in robotics is to use the so-called proprioceptive actuator, and it's just a concept invented by the guys at MIT, and the concept is to have low gear ratio gearbox and a high torque density motor. So normally it's a direct drive motor, a motor that can create quite high torque. And because of the low gear ratio, we will see that the torque of the motor, the velocity of the motor is not reduced so much onto the load. And this kind of actuator, because of the low gear ratio, they have the capability to damp the impact, because they are sort of back drivable, so you can move the motor by moving the load. And they still have a very high dynamic performances because they don't have any spring in the middle. So the motor torque is perfectly is completely affecting the load and acceleration and accelerating the load without any compliance in the middle. So you can achieve high bandwidth control, and these are the actuators that are used in the Cheetah Mini robot. I don't know if you ever saw this quadruped. It's doing quite fast motion and running and jumping, and you can show in this. You can see in this table the comparison between the traditional electrical motor that achieves, for example, a bandwidth of 5 Hz and is not robust to impact. This in case I think of a gearbox actuator with a big ratio in the gearbox. Then you have a series elastic actuator that can cope with impact, and the proprioceptive actuator that can reach up to 100 Hz of force bandwidth and is also able to cope with impacts. Finally, there is another class of very small, this doesn't work. Yeah, doesn't matter. It's like another class of actuators. I think Professor Marco Fontana here at Trento is teaching more about this, and these are piezoelectric actuators that are very small. They can do little motions, but they can be useful for very small robots like this one, the size of a coin, and it's an option in for small scale robots actuation. Everything is clear? Do you have any question on electrical motors? Okay. Then we can go on in the next slides that are on electrical, completely focused on the electrical actuators. Can you see the slides, Octavio?
Yes.
Okay. So in this batch of slides, we will give some useful notion of physics, especially the notions that are useful for describing the internal operation of electrical motors. Then we will see in detail the differences between synchronous motors and induction motors that we briefly introduced before. And then we will focus on DC motors, their principle of operation, difference between brushed and brushless motors, and how to derive the mathematical model of a DC motor, how to characterize the steady state response and the steady state characteristic curves, torque and speed curves of a DC motor, and then how to implement voltage and current control for a DC motor. First law we want to recall to understand the working principle of DC motor. It's the Biot-Savart law that tells us that a wire with a constant current flow generates a constant magnetic field around it. This magnetic field, it reduces with the distance. Then we have the Lenz law, that's also called the principle of action and reaction in electromagnetism, and tells us that when a closed conductor like a coil, as for example, is placed in the middle of a changing magnetic field, then there is an induced current that is produced in the conductor, in the coil, by magnetic induction. And this current that is produced in the coil produces on its behalf a magnetic field that opposes the direction of change of the magnetic field that produced that. So if you have an increasing field in the coil, then the coil will generate a current to create a field that opposes the increasing one. And the value of this current can be obtained. This current is generated by a difference of potential, by a voltage that is called electromotive force, or EMF, and is computed by the Faraday law that tells us that this EMF voltage on the coil is equivalent to the opposite of the derivative of the flux, where the flux is the amount of line of magnetic field that pass through the surface. So if you do the integral, surface integral onto this coil, you can compute of the magnetic field onto this surface, you can get the flux. So the flux will be highest whenever the lines are perpendicular to the coil, and will be zero whenever the lines will be parallel to the coil. So the variation of this flux could be, for example, not because B is changing, but because we change the position of the coil with respect to the to the magnetic field. So let's think we keep the magnetic field vertical, fixed, and we move the coil. We see that the flux will be varying. And an electromotive force, if we take the put a multimeter, a voltmeter at the terminals of the coil, we will see that a voltage will appear according proportional to the velocity we change the flux. So if we move the coil very fast, the voltage will be big. And we call this voltage back EMF because it's a reaction, as we said, to this motion. Then the last one that we will use is the Lorentz force law. And that tells us that if we put a conductor of length dl, let's say is infinitesimal conductor for now, that is traversed by a current, and we put inside a magnetic field B, then a force will appear on the element that is this expression. So is the cross product of the current times the magnetic field. So you need to think about the with the right hand rule to work out the cross product output, and you put your thumb as the current and your index, how do you call that? Well, the second finger along the B, and the third finger will be the force direction. And if you integrate along all the conductor, you have the total force that is generated on the conductor. That is L, length of the conductor, times I, the current, cross B. So I here is a vector just because tells us the direction of the in which the conductor is oriented with respect to the field. Everything's clear? Okay, so we come back to the AC motors, and they normally are powered with three-phase alternating current. As we said, three-phase alternating current usually 380 volts. But 380 volts, what does it mean? Well, do you know what 380 volts represent? When we talk about 380 volts, is the amplitude of the sinusoids. So we have three-phase current, alternating current available in the industry, for example, in your lab. And this means that we have three phases, three conductors. We have a plug with three conductors, and a fourth one that is a neutral, and a fifth one that is the ground. But these three conductors, they have a sinusoidal voltage, and this sinusoidal voltage are have an amplitude. And do you know how much is this amplitude? Is 380? 220. No.
220 times square root 2 square root 3. That is a three-phase.
Okay, because 380 is the root mean square. So it's like if you have a constant voltage and the power provided by the three-phase, it will be as we provide a constant voltage of 380 volts. But yeah, that's just a detail. The important thing is that three voltages will be generating a magnetic field in the motor, in the stator in the particular, and this magnetic field can create two or multiple poles, and where each pole is a pair of winding. For example, this is creating a north and a south pole. This is another one. It's creating another north and south pole, and this is another north and south pole. And the thing is that because of the three phases are under 20 degrees delayed one each other, then the sum of these poles will result as a single north pole that moves around the periphery. And the number of poles is usually a multiple of the number of phases. That, as I said, is usually there are three-phase motors, and more poles result in lower rotational speed. We will see better this later. So if in general, in the case of a synchronous motor, you have a rotor that is a permanent magnet, or is a coil energized with constant current, this will create a magnetic field in this direction. This is the rotor coil or the permanent magnet. And while the stator, the effect, the overall effect of the statoric coil are creating a magnetic field that moves this way, for example, and put in rotation the motor, because the south of the motor is attracted by the north of the statoric field. And they rotate at the same speed. This is why they're called synchronous. So if you apply these three-phase sinusoidal voltages to the statoric coils that are spaced spatially on the stator at 120 degrees and are spaced there potentially spaced temporally with sinusoid of 120 degrees delay on each other, this voltage produce sinusoidal currents that summed up in a certain way can create a magnetic field, so two poles that are moving around around the periphery of the stator, and they drive, as in the case of a DC motor, they drive the rotor. And I can give you an insight into this if you consider, for example, like a circumference, and you take a point on a circumference of or radius 1, then you have that the x component of this x projection on this axis is the cosine, and on the y-axis is the sine. And if you move this point around, you can describe the motion of this point as a cosine and a sine. Okay. So if you do the same for two coils that are 90 degrees, and you provide, for example, for this coil, you provide a cosine, and for this other red coil that is at 90 degrees, you provide a sine. You are generating, in essence, a magnetic pole that is moving at frequency omega. So you see here that with two phases located at 90 degrees, powered with current or voltages that are shifted 90 degrees each other, because cosine it's 90 degrees anticipative with respect to the sine, then you can create a rotating field, a magnetic field that rotates. And the same thing works for the free phase case, with free phases shifted under 20 degrees rather than 90. And as I said, the rotation, the motion is based on the attraction and repulsion of the magnetic poles that the statoric field generates and attracts the closest permanent magnet. So the south is attracted toward the north, and then the north moves here, and the rotor starts to move. The north moves here. And while a permanent magnet has only two poles, the stator can be wired such that the magnetic field has a higher number of poles. And the number of poles refers to the magnetic poles. So the number of north and south that appear on the surface created cutting the motor perpendicular to the shaft. So on this surface, you see here that we wired up the coils, creating a pole, a south pole here, a north pole here, a south pole here, and a north pole here. The other, you need to think about whatever we saw before on the whole periphery of the free phases. This will be happening only in one half of this circumference of the motor. So instead of two poles, magnetic poles, we have 4 poles for one turn of the rotor. Therefore, whenever the rotor completes one rotation, we have a switch of polarity that is double than in the 2-pole case of a motor of 2 poles. And this means that the rotor speed it's slower than the statoric field, and while the statoric field speed is correspondent to the frequency of the supply, so the frequency we talk about, I don't know, 50 hertz, for example, then the speed of the rotor will be this frequency divided by the number of pole pairs. We saw that with 4 poles, we have 2 pole pairs. So the frequency, the speed will be half of the frequency. So with a 4-pole motor, the speed of the rotor will be half of the frequency of the supply currents, and with 8-pole motors, the frequency, the speed will be 1/4. And one way, as I said, these kind of motors are used mainly for applications like fixed speed, but you can change this speed by changing the frequency of the supply. And these synchronous motors are mainly used as generators. So if you do the opposite of what we do, rather than supply energy and extract and produce, transform it into mechanical power, you move the shaft, you apply a torque to the shaft, you can generate electric energy. So these motors, they are bidirectionals. All the motors actually are bidirectionals. They can work as generators. Just you need to be careful to apply a torque on the shaft, and the motor will regenerate electrical energy. And small synchronous motor are used, for example, for tape recorders, and the capability is that they can have a very high efficiency. They work a very reduced amount of speed, but they are very efficient. While the induction motor, well, also a synchronous motor, we said that as a rotor that is not energized, and the fact the energy in the rotor comes from the statoric magnetic field itself that couples on the coil, on the rotor coils, and induce a current in it, and this current on its behalf creates a magnetic field that is opposed to the statoric field, and the interaction of these two magnetic fields creates a torque. So whenever so there is always the rotor will be turning slowly, always lower than the statoric field. Otherwise, you don't have enough induction and flux coupling, variable flux coupling into the rotor. And the difference in speed is called slip, and is proportional to the generated torque. So in the case, for example, the rotor turns at the same speed of the statoric field, that you won't see any changing magnetic field, and so you won't have any torque. And the slip and the rotor speed can be related this single equation, where omega sync is the speed of the statoric field that is related to the frequency of your AC supply. Everything is clear? We can do a break now if you think you're out of the class. Then we start with the principle of DC motors. 10 minutes. Okay.
Professor,
Yes.
we can't hear you.
Yeah. We didn't start yet.
Okay, sorry.
Okay. So let's talk about now on the principal operation of a DC motor. Remember the Lorentz law that we saw, and in this case, let's consider a simple case where we have a statoric field constant and a coil on the rotor that is supplied with a constant current. Okay, constant current, and each side of this coil, I will show you again the animation. Sorry. It's whenever the current in the coil you see is shifted every time, every half turn. And if you look at the Lorentz force that is generated on the coil, whenever the current is running in one direction, the force, there is a couple of force that is generated that creates a torque. And whatever, if you look at the coil, the force that is generated orthogonal to the axis of rotation on the sides that are orthogonal to the axis of rotation. So if this is the coil that is rotating like this on this side of the coil, then this force, it's since the magnetic field is always vertical, this force will be along this direction in one segment and in this other direction in the other segment. And these two forces will nullify each other. While the forces that are generated because of Lorentz law on the side of the coil that are parallel to the axis of rotation, they will generate two forces, one in this direction, the one in the other direction, that will create a torque that will make rotate the coil. But these two forces, when the coil is completely flat, will be creating no torque anymore. So the trick of a DC motor is to reverse the current and allow to create again forces that continue the motion. And the element that does this is a commutator. So each half turn of the coil, the commutator inverts the current direction, as you saw in the animation, changing the orientation of the rotoric magnetic field that will be continuously tracking the constant one from the stator. So you think about changing the direction of the current will flip the magnetic field, and the south become the north, and the north will become the south, and then you can continue turning this way. And of course, this force the torque is bigger when the coil is vertical, and is zero when it's horizontal. So you can have a torque that is not constant, and there is a torque ripple. So you see that the torque along the motion is non-constant and is rectified because of the commutator, but is something like a half sinusoid, the absolute value of a sinusoid. And this creates a torque ripple, the Coggin torque that we saw in the lecture on the disturbance signal, and it can be mitigated by using more pole pairs. So rather than having one coil on the rotor, or in this example, we have more, and each one is creating a pole, and you have that more poles, they create less torque ripple. And the way the power is delivered to the rotor, in the case of a brushed DC motor, is using the commutator and two brushes. So the two brushes are energizing the commutator, and the commutator is just a set of conductive elements that are connected to the coils in a way that the current in the coil is shifted at each half turn, for example. So the brushed DC motor use mechanical design to switch the polarity on the electromagnet of the rotor, and you see that these brushes are creating these sparks and create friction. They are wearing out after a while. You need to replace them. And also they can create electromagnetic interference on the environment surrounding them. And these were the sparks generated by the commutation. Instead, the idea that they got recently, last, I think, 30 years, is to use permanent magnet on the rotor rather than a coil, and also on the and a coil on the stator. So before we saw was a permanent magnet on the stator and a rotor on the coil. Here is the opposite, and there is no need this way because the permanent magnet by itself doesn't need to be energized with current. It creates a magnetic field by itself. We don't need the brushes and the commutator to switch the polarity of the rotor magnetic field. But how we achieve the same result? We need to do the commutation in the stator, and we do this commutation electronically using, for example, the position, the rotor position feedback to determine which of the coils needs to be switched, energized at each time. And this position feedback, we saw the Hall sensor and or rotary encoders. They are a way to detect the position of the rotor. And so each coil of the stator is controlled separately, and they're switched on to attract or repel the permanent magnet of the rotor. And they are called DC motors because, differently from the AC motors, the coils of the stator that are usually also three-phase, so there are three coils around the periphery, they're powered by a constant voltage, not a sinusoidal voltage. And the magnetic field that it's coming out as a waveform, a trapezoidal waveform, not a sinusoidal one, but it's still a rotating magnetic field, okay? To continuously rotate, the current in the stator coil must change continuously, and a proper feedback loop is needed to properly switch the voltage on the stator coils. You see this little animation that the coils are energized according to the rotor position. Therefore, brushed DC motors are more complex. We see why they are more complex. They need more complex electronics to vary the polarity of the coils. Then, as a comparison, the brushed DC motors, they have low construction cost. They can be rebuilt. The brushes needs to be replaced. They have simple controller. They just slow down when the voltage is lowered and spin in the other direction if the voltage is reversed. You can achieve high torque even at low speeds, and they're ideal for extreme operating environment. But the problem is that, as we said, there are sparks, there is friction due to the brushes, and the brushes wear out quite fast. While the brushless motors, they have less maintenance due to the lack of the brushes. They operate effectively at all speed, at many speeds, so they are used for variable speed application differently from the synchronous motors, and they have high efficiency and high output power with respect to the brushed motors, and low electric noise generation, but have more complex controller. Everything is clear till now? Okay. Now that we gave this introduction on the working principle of the DC and AC motors, we can have a look to how do we model, for example, a DC motor. This is the only one we will provide a detailed model. Because the model of an AC motor requires a whole course on electrical machine of at least 6 credits. It's very complex. And as a simplest case, we consider the case of a monophase DC motor, so not a BLDC 3-phase one. We don't care at this point if the permanent magnet is in the stator or in the rotor, but we just know that we have a permanent magnet and we have one coil. So remember that we assume we are in the linear domain, so away from the maximum current and voltage limits. And we know that we have, because of the Lorentz law, we have some torques generated due to the current. But we also have, if you remember the motion of the coil inside the B, there was a coil moving in the magnetic field, so there was also a back EMF. Because the magnetic flux is changing in the coil due to the rotation. So if you do an electrical balance, that is applying a Kirchhoff law on this loop, let's say we are powering the coil of the motor with an external supply voltage. We have that the supply voltage of the coil, it's equal to the drop in voltage across the resistance, where R is the resistance of the coil, of the winding, because we have a conductor, and even if it's a wire, it's very long, has some section, so its resistance is non-zero. So as some value, very low, a few ohms, like 7, 8 ohms or 10 ohms, not more, but there is some resistance. So there's some voltage drop on that. We have an inductance because we have a coil is winding many times, you know. So the inductance will be proportional of the inductance of the coil will be proportional to the number of turns. And you have many turns on a coil of an electrical motor, so the inductance is quite high. And do you know what the inductance does? What is the peculiarity of the inductance? Sorry?
I don't remember.
So the inductance, it's creating a voltage that is opposing to the changing current. So it's opposing to, it's like something that opposes to the big change in current. So let's think you are from 0 to 12 volt powering the battery here, and the current, if you have a resistor, will be immediately, let's think you have a resistor, the current will be immediately going to the value given by the Ohm law, that is volt, 12 volt divided by resistance. But if you have an inductance, the current cannot change instantaneously. There is the current becomes a state variable, and there is a derivative on the current, and this current will increase smoothly, continuously, without abrupt discontinuities. And this is due to the inductance. But we have also the drop on potential due to the back EMF, that we said that there was a variable flux, and so there was some variable flux proportional this time to the is due the only, since the magnetic field in a DC motor is constant on the stator, for example, in the example before, then the only variation is due to the velocity the rotor turns, that creates a changing magnetic field. And so we can say that a back EMF is proportional to the angular velocity of the rotor via a constant kV. And this constant is called the back EMF constant. While on the same line, if we think about the rotor, this will be coupled with a load, because we have an actuator that is usually connected to the link. And if we write a mechanical balance on this load, we write in essence Newton law on torques. We have that the torque generated by the electrical motor, it's equal to the acceleration, angular acceleration of the inertia of the load, which is represented by the inertia Jm, plus what? What is this?
Damping effect.
Due to what? To as the student here properly replied, the damping is due to the friction. In this case, viscous friction. So it's a torque that is proportional to the angular velocity, increases with the angular velocity. Plus, we have the load torque. So we have I don't know, some external torque that can be also applied on the shaft, and let's think about there could be some gravity torque or some pulling torque here, and then we need a way to connect the mechanical domain to the electrical domain that we saw separately now, apart from this connection with the angular velocity. And the connection is given by the Lorentz law. We said that current passing through a conductor immersed into a magnetic field is generating a couple of forces, and that creates a torque. So the proportionality between the torque, the motor torque, and the current is given by k tau, that is called the torque constant. And we can see here that there is an equivalence between the motor, the back EMF constant kV, and the torque constant kt. And this equivalence comes from the conservation of energy. We know that energy conserves, so the input electrical power transforms into losses and mechanical power. And the input electrical power, it's the supply voltage times the current. Then we have, if we consider the previous equation of let's say in here we are neglecting the effect of the inductance, so we have only the drop on the resistance. So we have Ri times I, Ri squared, plus the back EMF times I. And we know that these are the Joule losses. So it comes that this part of the electrical power, it's the one that is transformed into mechanical power. And the mechanical power, you know, how does it look like?
Force multiplied by velocity.
That in the angular case becomes?
Torque multiplied by angular speed.
Exactly. So torque of the motor times angular speed. And if we replace the previous expression, which is tau m equal to k tau I here, and VB kV omega here, we can see that we have an equivalence of kV and k tau. And we call this now on k. They have different unity of measure. One is mapping tension into an angular velocity into a tension, into a voltage, and the other one is mapping current into torque. But they have the same value. And now that we introduce the mechanical model in the time domain, it is also convenient to transform this mechanical model that is based on differential equation, first order or second order differential equation in the case of the mechanical part. It's convenient to transform this into algebraic equation in the Laplace domain. And why do we want to do that? Because we want to compute the transfer function. The transfer function is nothing more than an input-output relationship. So if I have the voltage as input, having the transfer function, I can compute the response of the velocity of the motor or the position of the motor, for example, depending on which output I choose. And I can compute a transfer function from each input to whatever output I select. And I quickly recall for the ones that already know that, or the ones that didn't have any control background, just consider this. The Laplace transform is to map a differential equation into Laplace domains. We replace the derivatives with S, where S is the Laplace variable. And to distinguish between the time domain and the Laplace domain, we have capital letters for all the relevant variables, input and outputs. So if we look at the previous one, we have R times I plus RL di over dt. Di over dt is replaced by S, the d over dt, and we can collect this way I. And we have the back EMF that is proportional to the angular velocity. From the mechanical balance, we can do the same. We have omega dot that is represented as this S times omega, and the omega itself on the friction, it can be collected this way, and we have a load torque, sorry. Then we have the Lorentz law that maps current into torque. And if we want to write a block diagram of this that we will use to compute the transfer function, we can see that we can do it easily because we have the input voltage, we subtract the back EMF, then we are left with this times I, we divide by this. This is the block that represent the electrical dynamics. Then once we have I here, we multiply by K and we get the tau M. Then we remove from tau M, we subtract tau L with this summation point. and we are left with this term. We divide by this, that it represents the mechanical dynamics, and we obtain the output shaft angular velocity. And as you know, we can, by integration, getting the angular position of the shaft. And in a Laplace domain, if derivative is replaced with S, the integration is represented by 1 over S. So multiplying by an additional block, 1 over S, we can map from angular velocity to angular position. Then the angular velocity multiplied by K, it's the back EMF that is feedback here. So the back EMF acts as a negative feedback in this system. And if we want to compute the transfer function of the coil to the angular velocity, so from the voltage on the coil to the angular velocity on the shaft, we in essence, this is take it like this. We need to compute the open loop transfer function, multiplying all the blocks on the forward line, divide by 1 plus the back loop, the feedback loop gain times again the open loop gain, and the result is this. We will see this in the control part more in detail. I don't know if you ever seen this. Who saw this kind of approach to compute the transfer function before? Okay. Yeah. So depending in the case of this is the transfer function on the voltage that is so is the relationship between the output that we choose, for example, the angular velocity and the input voltage. But if you select as output the position, we will have 1 over S multiplied by this. So we have the same transfer function times 1 over S. And we can write these transfer functions in a way that make explicit the time constant. And we will see that if we make explicit the time constant and we see how do they look like, we can simplify our model. And if you, in essence, let's consider this transfer function from voltage to angular velocity, you collect the resistance, you get L over R, that is the electrical time constant. While if you collect the BM from the mechanical part, you get JM over BM, that represents the mechanical time constant. And this, if you look at the values of these guys and you take a data sheet of a motor, you will see that the electrical time constant is much smaller than the mechanical time constant. Because this is, I think, is millihenry. Usually is in the order of millihenry. Henry is the unit of measure for inductance, while this is, as I said, 10 ohms. So this electrical time constant is below 0.1 milliseconds, or stuff like that, while the mechanical time constant is much bigger. So we can simplify if we develop the product of this time constant, we get a second order polynomial. And if tau L is, let's say, 0, we can remove, if we have tau L much smaller than tau mechanical, then we can neglect this term, remove this one, and we end up with a simplified model transfer function that is only first order. We see there is only one time constant. It will be slightly different from the mechanical one because you need to collect this to compute the time constant form, because you need to have 1 plus S time constant. And the system becomes first order system. And if you do the computation by yourself at home, you can get the first order system as this transfer function. So, and suppose that you have a constant voltage applied, and this is a simple that know for the ones that already did this kind of analysis. There's a question: which one of the three is the correct one? So if I have, let's say, this transfer function, and I give a constant voltage step input to the voltage, which one of the three is the right one? The three plots is the correct one, in your opinion? I give you a help. You can use to do that a very useful theorem. It is the final value theorem that allows you to analyze what happens and the steady state whenever t converges to infinity. So after infinite time, what is the value of the output? So this is the limit of S converging to 0 of S GS, that is the transfer function times US. And the input, as we said, is a step input. So it's the Laplace transform associated to the step input is 1 over S, and 1 over S will simplify with that. So we are left with the GDS, and we want to compute the limit of GDS for S going to 0. And if you replace 0 here, you have 0 here, you have a number, you have 0, and you have one number over 0. So you have infinite. While in the case of the velocity, you have 0 here, you have 1 over a number times a number, and it's a constant number. So it means that a steady state velocity goes to a constant value. So this is wrong because the position diverges, because what happens if you apply a voltage, your motor starts to turn, and the angular position, if you keep the voltage constant, it will increase infinitely, okay? While the velocity, after a while, will reach to a point, constant point. That is whenever your voltage it's equilibrated, the torque generated by your voltage is equilibrating friction. So the rotor starts to accelerate, and then at the beginning, and then after a while stops accelerating, goes a constant speed. So this is the correct value, and this is the wrong one, because here it tells you that the speed is increasing indefinitely. And we will see now this more in detail. To control an electrical motor, there are two ways. One is to adjust the voltage or adjust the current. And if we consider the voltage control, let's for now ignore the dynamical component due to the inductance. And we see that you apply a voltage, and we have a back EMF that depends on the velocity, and the current is the applied voltage minus the back EMF divided by the resistance. And this current creates a torque. And if you have this torque, let's assume that the motor starts at rest, and this current flow creates a torque that starts to accelerate the motor, and the motor speed starts to increase. But as the motor speed increases, we have a back EMF that also increases. And when the back EMF increases, it reduces the available current, because the current is the difference between the back EMF and the voltage. So at some point, we will have that the back EMF will be equal to the voltage, and no current will be flowing here anymore. So we will have no torque applied on the shaft, and the motor will stop accelerating and keep at constant speed. In reality, we saw that there was friction. So, and this constant speed, sorry, it's the voltage divided by the K, because we said that the voltage was equal to the back EMF. In reality, in practice, there is a friction also that plays a role, and this makes this steady state velocity, angular velocity, smaller than this value. So with a constant input voltage, after a transient, we reach a steady state situation where the motor stops accelerating, because the motor torque, it's all balancing friction. Or if there is an external load, also the external load. And you see here that whatever we saw before, this is the position that starts accelerating at the beginning and then increase continuously at a constant rate, because the velocity reach a steady state value. And the current is here compensating the friction. And this is this is the constant step input voltage that starts from 0 and went to I think I don't remember how much was that, 28, no, 25. Anyway, this is the plots that are generated by the code that we will use in your MATLAB last session. And we see that motor velocity and current are constant to steady state. And this steady state response is useful to derive the static characteristics of the motor. And the static characteristics of the motor are the steady state velocity and the capability to balance a load torque. Steady state means that the derivative of velocity and current are 0. So from the electrical dynamics, we can compute, if we set this time, we consider also the inductance, we set it to 0. We are left with this relationship. While for the mechanical balance equation, we can get this relationship. And this is an algebraic system that we can solve. First, we solve for the current. We compute the steady state current, like the voltage minus this, divided by the R. And then we replace this I inside the mechanical balance equation, and we can compute the steady state angular velocity. And the steady state angular velocity has this expression where we have a constant input voltage, we have K that are parameters of the robot. So we have this constant plus something that depends on the load. And what does this equation represent, in your opinion? Is it linear? We want to compute the dependency of this steady state velocity with respect to the load torque. So to the torque that we want to be able to generate for our actuator, for our link, to move our link. This is like, is it linear? So omega is linear with tau L. Here we have a constant. Do you see what is this? Omega is proportional to tau L or inversely proportional? Yeah, it's inversely proportional. It is a minus sign. And in essence, we have a constant plus a constant times tau L. So we have a line, we have a linear relationship, and we have a line that is this way. So if tau L increases, so if tau L is 0, we have the maximum velocity. Then if tau L increases, we from this constant we subtract a bigger value until we go to 0. And this line will move according to the supply voltage. And this is the famous velocity to torque, load torque relationship of a DC motor. And I report this to relationship here to analyze. And what we want to do now is to characterize the point, the relevant point, the extremes of this curve. And all the operating point of our DC motor will lie into this line. So if you have a no load, we will be here, no torque load. And if you have increasing the load, the operating point will be, the speed will reduce. So this is the speed we can achieve with a certain supply voltage given a certain load, till there is a way in situation, stall is called stall situation, in which there is no motion and all the voltage it's used to generate the current to overcome to create the torque load, the load torque. And these two points in the steady state relationship, let's start to compute them, starting from the stall torque that represents a point on the graph where the torque and the current is maximum, but the shaft is not rotating. That corresponds to the maximum load situation that our motor is able to sustain. And to do so, we set omega to 0. From this equation, we can get the numerator equal to 0, and we can compute the value of the torque by kV over R. And this is the stall torque, maximum torque we can achieve. While the current, it just replace, so we can, from this relationship, we replace omega to 0, and we get V over R, which is the stall current. And this is a situation wherever we have constant current, we have no motion, so no back EMF, so all the voltage is dropped on the resistance and it's creating the maximum current. So this is a stall torque, and this is the stall current. This is the current curve. Instead, the other point is the no load velocity, which is the maximum output velocity of our electrical motor when there is no load torque applied on the output shaft. And so in this case, we set the output load torque to 0, and we get this expression for the no load velocity. And if we collect R here, we get this expression. And if you remember, this was the stall torque, so we can relate the no load velocity to the stall torque with a certain proportionality. And if we neglect friction, then this simplifies to V over K. You remember the 3 slides ago, or a bit more, we were saying that the no load speed, it's whenever the all voltage is equal to the back EMF. So in case of we neglecting friction, this is the value of the no load velocity. And instead, for the current, we use the mechanical equation, setting the tau L to 0, and we get simply the friction torque divided by K. And what we said is in the no load condition, we have that the current is balancing friction. So if you let spin your motor without any load, this will accelerate to the steady condition that is said before, and we arrive to a point in which the torque will be the one that is the motor torque will be equating the friction. There will be no more acceleration, and the current it will be the one that is necessary to create the torque to overcome friction. If you apply a load, the motor will slow down and work in another operating condition that is in the middle. So these are the no load velocity, no load current. Whatever is in the middle is the operating point you can use in your system. And if we want to compute the output power, we the output power diagram we should consider as the input electrical power. We have again the voltage times the supply voltage times I, that becomes this. We see that here the Joule losses, the electromagnetic power that is needed to magnetize our coil, which we can discard, we can neglect. And here, whatever we said, that was the mechanical output power. And we see some of the power is lost in Joule losses in the winding, while the rest is converted into the mechanical power. And assuming a constant voltage, knowing that the current is equal to tau m divided by k, we can, from the electrical part, can compute the value of steady velocity. Now we are not considering the torque on the load, we are considering the torque of the motor, because we are interested in characterizing how good is the motor to convert internally electrical power into mechanical power. So we are concerned about the torque of the motor shaft, not the load torque. And if we multiply this steady velocity for the tau m, we get a quadratic relationship. And this is the relationship that relates the output power to the mechanical motor torque, sorry, of the motor. And do you know what kind of function is this? If you consider tau m as the incognita, there's no known. You have a square here. Exactly, it's a parabola, and the convexity is up or down in the parabola. Yeah, up, it means that if you have a plus on the coefficient of the quadratic term, but if you have a minus, you have the concavity down. And so it's a parabola with concavity down, and to get the maximum power, we need to compute what? Oh. How do we find the maximum of a function?
The first derivative, and then search for the point equal to 0.
Okay. Yeah. Let's do that. So we compute the derivative about tau m. We set it to 0. And then we compute the value of tau m for this. And we see here that we have some simplifications. And again, we have the stall torque. And we see the optimal point is the one that is half of the stall torque. So the maximum transference of power is for the half of the stall torque. Well, here we consider tau m and tau l equivalents now. We are just neglecting the load now, considering only the electrical part. And okay, we know this is not enough to say that is like a maximum. We should see that the second derivative is positive because it could be a minimum. But if you compute the derivative of the derivative, you see that it's a positive number, and so we know that the point is a max. Otherwise, this tells you only this is a stationary point. It could be a maximum or a minimum. So you need always to check the second derivative, the action. If we replace in the previous expression of omega, again, this tau m with this expression, we have simplifications, and we see that omega is equal to half of the no-load speed. If we neglect friction, we have this. So the maximum transference of power is for half of the no-load speed and half of the stall torque. And this is makes sense because if you consider power as the area under the torque velocity curve, we see here now the torque and velocity are flipped, but it's the same. The area here is very small, so we have small power here. The maximum area is here in the middle for no load, half no load speed, that is no load speed, and half stall torque, that is here. And again, in this point, the power reduces. But despite this, the electrical motors will be rarely operated at the maximum output power, because this operating point usually creates problem of overheat. So the Joule losses that we talked before, they are just waste of energy, and nothing is lost. So this energy transforms into heat, and the heating is not good in a rotor because the temperature increases and can lead to loss of insulation. Okay, I would stop here because the next one, I don't know if you want to do the last. There are still no, there are still a few slides. I will stop here before the efficiency part because it's more complex. Or if you want, we can do the efficiency, or we can continue next week. Yeah, let's continue. There's still 10 slides to go, and it's fine. Let's continue next time. And next time I will finish the actuator part. So we will see also the simulation, how to simulate our model, and how sorry. We see also all the chapter about transmissions. That is, how do we convert the torque of our robot, of our actuator, sorry, into a torque that is the one that is needed to operate our robot. So let's say we have a small motor that produces a small torque. With a gearbox or transmission, we can amplify this torque. And we also talk about some non-idealities like Coulomb friction, viscous friction, and stiction that are present in the actuators and needs to be considered in the simulation to have a realistic simulation of the system. Okay. Is there any question from the people online? Okay, so you should all have found the instruction to install the virtual machine on the Moodle, and please install MATLAB. I think we are using we are using version 2019B. So you can use either that one or a more recent one. You will able to open the models. If you have an older one, the models unfortunately are not retro compatible and they cannot be opened. So let me know in case we need to find a solution using another MATLAB. But that's it. Okay. See you next week.